Welcome to this NCTS Distinguished Lecture and also a physics colloquium. We are very happy to have Professor Misao Sasaki from Japan, and he was a former director of Yokohama Institute of Theoretical Physics. He retired this year, and now he is so energetic, so he continued on, and is now the deputy director of IBM in Tokyo, and he will be there and serving the international community. Misao is a famous cosmologist. Throughout his life, he has worked on many different topics in cosmology, from inflation, and now he's stepping into gravitational wave cosmology. And apart from research, he has also has many excellent students in his life. Some of the students are also here today. Yeah. I think he has a lot of exciting things to tell us today. So I will hand him.
Thank you. Thank you for a very nice introduction. And so today I will talk on this topic, gravitational wave cosmology, which probably is kind of a new word or new terminology, because usually it's just called gravitational wave astronomy. But since I'd like to focus on cosmological aspects, I mean, not really focusing on, but to emphasize some of the cosmological aspects, I sort of made up this word. And so if you like, this will be the Chinese version. And if you can use it in your papers, I'll be very happy. Okay. So by the way, so as they said, that because of this detection of gravitational waves, now we are entering the era of gravitational astronomy or cosmology, and dawn is arriving, and it's quite an exciting time. So let us first introduce, talk about what are gravitational waves. Probably many of you already know, but let me just give you a brief introduction. And actually, as it says, that this is the only equation I have in my slides. And if you are looking for something more sophisticated, maybe you can ask me after the lecture. Anyway, so the whole point is that gravitational waves are ripples, so-called ripples of space-time, and propagating at the speed of light. This is an important sort of aspect, and predicted by Einstein in 1916. So it's about 100 years ago. And the gravitational wave will be emitted when there are some energy momentum or energy essentially is undergoing some random, very violent motion. And then quite a large amount of the energy can be emitted through gravitational waves. This is quite, actually, we will just see that this is the most energetic phenomena in the universe. But anyways, so when you have some random motions or very, very violent motions, then those waves will be emitted, or the space-time will be disturbed or perturbed, and these perturbations propagate. And they propagate by stretching and contracting space perpendicular to the direction of the propagation direction, and this is called the quadrupolar nature of the waves. So it's like you stretch, for example, if this is x arm and y arm, then you stretch x, it shrinks the y, and stretch x, y, shrinks x, and this continues, and this and propagates. And the equations for that is this small hij is a perturbed so-called spatial metric. Thank you. Yes, component, and this c is the speed of light, and this is the called a Klein-Golden equation. But anyway, this represents the wave propagated on this velocity c. And in our case, this c is just the velocity of light. And it has this divergenceless and traceless conditions. These are the condition this HSA satisfies, and this implies that the waves are transverse and traceless. So this means that when you propagate towards, say, z direction, then only independent component will be the x, y components. And if you take a trace must be 0. Okay? So this is how the things propagate. Now, if the actual gravitational wave disturb or the stretch the space like this amount, that will be easily seen. But the problem is, of course, this is a maybe exaggeration by the factor of 10 to 22. so in that sense, it's very, very difficult to measure. But this actually means, oh, sorry, the other point is that because it's simply how to say, propagating disturbance of the space-time, and the space-time, I mean, which is described by the Einstein theory, and Einstein theory, as you know, is the theory of gravity. Therefore, their interaction with matter is always through the gravitational coupling constant. And the gravitational coupling constant, as you know, is very, very small. So because of the smallness, the interaction is so small that it can essentially penetrate anything, any whatever the matter is. So as a result, for example, if you take a look at this famous kind of diagram of history of the universe, where the horizontal axis represents the time, and vertical is kind of the size of our universe. So in the beginning, we have some kind of big bang, which we don't know what it is, but anyway, and then we have so-called the era of inflation, where the universe probably expanded exponentially, very fast. And after that, the universe will be reheated, and usually what we call Big Bang theory, or the theory of our universe, where our universe started with very hot and dense stage, starts right after this inflation. So in this figure, well, it doesn't say so anyway. So you can regard this epoch as the beginning of the Big Bang universe, or the start of the Big Bang. Anyway, then the universe will be a whole very hot and dense, and that as it expands, it cools down, and density becomes small. And then there is an epoch where so-called the last scattering surface, where it means that photons propagating in the past will be scattered many times because of the high density and high temperature. But after this epoch, they never interact with any matter, and the matter becomes neutral. And so this is the time when photons start to propagate directly to our eyes, let's say. So this is the place which is observed by so-called cosmic microwave background, and this is the limit of our universe, where we can observe by electromagnetic waves, because beyond which the electromagnetic waves interact too much with, so it's essentially a non-transparent kind of glass type thing, where when you enter the stage, so you don't see anything. But as I said, gravitational waves penetrate essentially everything. So if something happens here, and if something violent happens, and that produces gravitational waves, those waves would propagate to our eyes or to our detector without any obstacles. And so this means that if we have some means to detect those waves, we can actually see the very, very beginning of our universe. So this is a very, very special nature of gravitational waves, and which become very, very important in this century. Now, of course, that's one of the most interesting part of gravitational cosmology, but in general, because you cannot really go to that point from the beginning. You first have to look for where the gravitational wave generated, and where they come from, and so on and so forth. They look for some astrophysical sources to find. For example, this LIGO detector I will talk about, this is the sort of reason why they constructed such detectors and actually saw the gravitational waves. Anyway, so they are most promising candidate up to 2 years ago or so, and actually which turned out to be true, was so-called gravitational waves from binary neutron stars or binary black holes. Binary neutron stars are the binary system made of the 2 neutron stars. Binary black holes made of 2 black holes. You may have neutron star black hole binaries. In any case, you need some very compact, highly compact object. The reason why you need highly compact object is that then in this case, they will behave like a point particle until the very, very end. Therefore, when they produce some waves, you can have a sufficiently large amplitude of the wave at the very last moment when they collide each other. But if those are not neutron stars, but just, for example, like solar-sized stars, then much before this stage, they will just collide because their size is too large. So before the wave amplifies, they just collide and you don't see anything. So that's why you need some compact object to measure the gravitational waves. And this is the situation. And then, of course, I mean, this is the kind of simulations done before the detection. And the reason why they did, well, by the way, so this simulation was done for 2 black holes. Each black hole has 35 solar mass, means that the mass great of about 35 times the mass of sun. So it's very heavy to binary black holes. The reason why they did this simulation is because the LIGO detector, which I introduced soon, has the best sensitivity in this mass range. And that's why they just did this just for reference. They didn't think of even detecting them because they didn't think that they didn't know if there's such sources until quite recently, until we have measured these gravitational waves. The biggest black holes seen in, say, from X-ray observations and so on is about 10 times the mass of the sun. So this is about 3 or 4 times bigger than what we observe in astrophysics. So anyway, so this was a simulation, but we did have some good indication that the Einstein theory is correct and the gravitational waves are actually emitted from those binary systems. And this indirect evidence gravitational waves. This was a situation until this couple of years ago, and which was measured by measuring the timing of pulsar timing of from those binary pulsars. This system consists of 2 neutron stars, but neutron stars are not just stars, but they are also so-called pulsars, means that they rotate and that they have some magnetic field, and by which you produce electromagnetic pulses. And these pulses are very, very accurate clocks, and then you can see by measuring this, you can see how the orbital motion changes. And this orbital motion change is drawn like this. This is the time, this is the cumulative period shift, and the line is the prediction of general relativity, and the points are dots are the observed points. And as you can see, it's beautiful matching. And this shows that at least indirectly, I mean, this matches with the Einstein theory, and it's theory that the gravitational wave are emitted from those binary pulsars. And the emission rate and everything matches very well. And this was a very good indication that Einstein theory is correct, and there are some gravitational waves. And also, it's sometime later that they had even much better sort of a test of this system. And actually, the agreement with the Einstein theory is tremendous, because we have about, I don't know how many, 6 parameters or so, which all crosses together at one single point, which is the prediction of the Einstein theory. So anyway, so this was the situation until 2015. Everybody believed that the gravitational wave must exist. And they do exist, they believed, but nobody had seen, and they started to worry if we could actually really detect it. But then there was a news, actually the news was in the February next year, so after about half a year later, but there was lots of doom already, because about this detection. So actually, LIGO detected this gravitational wave by the black holes on 14 September 2015. This was, yeah, they are very, very lucky because this is just 2 days after they start operating. And actually, this operation was a test operation. So I heard that actually the first time when, and I will show you this signal, which is very, very clear. And even you can see from your eyes. And such a signal is not expected. So the people who actually found this first thing they did is to make sure that this is not test. I mean, they used to do, or still probably do, this kind of blind test. Right? Only maybe a couple of people in the very top knows what to do, and then every once in a while they inject holes. I mean it's a fake artificial signal, and to see if they can really catch it. Okay, so this is a sort of test of the pipeline of the data analysis, and so the first reaction is that they thought that this was just a test, but when they went to the top, they said no, we are not doing any test. so that was the beginning of surprise. But anyway, and as I said, actually each black hole mass is the solar mass, and which turns to be the range of the best sensitivity for this LIGO detector. This sounds about 1.2 gigalight year or 400 megaparsec. And as I said, it's the emitted gravitational wave energy is about 10%, or altogether it's by 5%, 5% of the total rest mass. This is a huge amount of energy. And if you compare this with the supernovae is constantly very, very extraordinary violent explosion. But this is 10,000 times. The energy is actually 10,000 times bigger. So it's really, really something which is the most energetic event. But even on this most energetic event, since gravitational waves do not interact with matter, essentially, I mean, as I said, it's suppressed by this gravitational coupling constant. So they just freely propagate, and you don't really see anything. So despite the fact that they do emit a lot of energy in gravitational waves, it's very, very difficult to measure. But they did measure. Now, let me then tell you about what LIGO is. LIGO is the abbreviation for Laser Interferometric Gravitational Wave Observatory, and they have 2 detectors in the United States, one in Louisiana and one in the Washington state. And so they were separated by about 3,000 kilometers. This is an important number. I will come back a bit later. But so 3,000 kilometers means that if you just travel a light by light from one to the other, it takes 10 milliseconds. Okay, so this is an important number, by the way. And this is each arm. You have this kind of two rectangular arms, and you have the laser traveling through these arms. And you have some mirror where you get some interferometric patterns, and from this pattern you try to measure a small sort of this stretching and shrinking of the space-time of order of 10 to minus 21. And how small it is just if you compute this delta L over L, this is 10 to minus 21. And if you put L to be 4 kilometers, delta A is 4 times 10 to minus 16 centimeter. And if you think of the size of the nucleon, you know, the atom, say hydrogen atom, not atom, sorry, hydrogen nucleus. Atom is much larger. Nucleon size is 10 to minus 13. So this is 1,000th. So 1,000 times smaller than the size of nucleon. And this small, tiny fluctuation can be actually measured. This is a surprising thing. But of course, this can be done because you essentially do the kind of, how to say, collective, observation of collective motion of the mirror. If you try to pinpoint the position of the atoms, nucleons, then of course you cannot never do this because it's too small. But since there are, as we know, at least like 10 to 26, 23, 4, 5, a number of nucleons and which constitute the surface of the mirror, so that's the reason why you can actually measure this small amount. And this is the principle of interferometer, which I took from some LIGO site, so I can show you, I think, probably, if it works, okay, good. So this is how it works. So as I said, when the wave propagates, it just stretches one arm or shrinks the other, and this continues. And then when the wave, sort of, how to say, two waves which are emitted from this laser go in and come back, they are on the same phase, you have the bright spot. If they are off phase, then you get a blank spot. So in this way, if by measuring this motion of this interference patterns at the detector, you see what kind of waves are passing through. Yeah. Yes, sorry. And this is the one they measure. So in the beginning you have this so-called inspiral phase this is actually the phase the Hulse and Taylor observed in the 1970s. And so you have this inspiral phase, and then when approaches to stars approach together, then they merge. This is the merging phase. And after merge, because their mass is so large, in its actually the first detection line case, because two black holes merge into another huge black hole. And black hole are so-called quasi-normal mode, and they behave like a bell. So as a bell, when you have the bell, you have boom, and gradually sort of amplitude goes down. This is called the ring down. So you have a merging phase inspiral phase, merging phase, and ring down phase. So this is the actual observed signal. As you can see, I mean, of course, you do have all the noise and everything, but since we know the noise spectrum, you can just taking out of a noise spectrum out of the signal is very easy. And so you immediately see this in your screen. So this is actually something they saw on this night or in the morning or whatever. Anyway, so and this is these two so this I think this blue line is the one measured in Livingstone, and the red one is the Washington. And if you put them together and adjust the time, then they find by adjusting the time to delta t with 7 milliseconds, they essentially merge together. So the signal is so huge, so you can see by your eye that actually you have some inspiral phase of merging and so on and so forth. And the fact that two detectors see essentially exact same phase, exactly the same signal, it means that this must be something which is not accidentally occurring in by chance. And at the same time, important thing is that this time difference, 7 milliseconds. I told you that actually this 3,000 kilometers means that it should take 10 milliseconds if the wave emitted from here to here. But if you have this waves which is propagating, for example, from this direction, then these two will be arrived. The wave front will be arrived to a detector at the same time. So in this case, if the wave is coming from this direction, you will have no time difference. Okay. On the other hand, if you have the wave coming sort of parallel to this direction of the two detectors, then you see them separated. Wave front will be separated by 10 milliseconds, meaning that in any case, the time difference between two events must be less than 10 milliseconds. And this is exactly what we see. So, so you saw this is 10 milliseconds, 7 milliseconds. Actually, this also indicates that from which direction they came. So they, of course, it's a very, very rough sort of, it's not really a very good angular resolution, but from this fact, they can also see approximately where those waves came from. Anyway, now you see this lower panel actually shows not the real signals, but the numerical relativity. So you can do the numerical simulations of all this binary black hole merging, and then from this numerical simulations you can compute the wave emitted from such system, and you see that this red line represent the numerically generated sort of one of the best, say, numerically generated signal, which matches with the actual observed signal to a very, very high accuracy. So this was the really amazing thing. Now, so this was only the beginning, and well, the LIGO actually in the first round they run about 4 months, September, October. So yes, I think it's about 4 months. Within 4 months, actually they saw 2 events and 1 candidate. So this is the number, actually, it's small, but it says GW150914. So this 15 means that this is year 2015, 09 means September, 14 means the date. So this just shows when you saw this event. And the next one is the LVT 1510 12 or something. So this is a October 12th, and their signal was not so large. So although they are pretty sure this was the event, they announced this as a real event data because the signal to noise ratio was just about threshold, like 10, about 10. Now, this is just one day after Christmas, GW151226. They saw another event, which is even smaller mass, but they saw, so even within this 4 or 5 months operation, they already see 2 plus 1, or 2.5 events. And after after a while, they upgraded the machine, and the sensitivity went up a bit. Then again, I'm not exactly sure how many days they did the observations. Probably like again 4 months or so. Yes, but anyway, so they saw 3 events. These are the solar mass. So in fact, what they have seen is that they have seen a very small mass, a black hole binary events. Two of them are small mass, which is about each black hole is about the size of 10 times the mass of Sun. But for the others, the mass scale is very large. It's like 20 or 30 solar mass. So these black hole events, it's amazing that they did not expect such events to occur in our universe because we have never seen a black hole this size until this this gravitational wave detection. So it is still a mystery, and maybe they are actually from very, very early universe. And this is one of the things which is related to so-called gravitational wave cosmology. So they may be just another sort of, how to say, result of some astrophysical processes. But there are indications that actually they may come from very, very early universe as well. Anyway, so I just found another interesting file from LIGO site. This is kind of, yeah, by the way, gravitational waves, this frequency is like about 100 hertz. And if you replace that with a sound, actually this is a kind of the sound you can actually hear, the human ear can hear. So they made this sound, and I think now you can hear it? Yes. Okay, so that's from LIGO. Thank you. So of course, I mean, this doesn't make any music, but it's amazing that you can actually hear what is going on by your eye. Now, this is the LIGO, and right now LIGO is again under new updates, and within hopefully they say that within a year, probably early next year, in 2019, they start operating the next one. And the next one will be much more, I'll say, the level of sensitivity increased by, I think, by a factor of 2 or something. And the important thing of gravitational waves is that this is a wave you measure. It's not the flux you usually measure in electromagnetic waves, but this is a wave itself. And as you know, amplitude of wave decreased 1 over r, where r is the distance from the source. So instead, in the case of flux, it's 1 over r squared, but this is a wave which just decreased by factor 1 over r. Now, this means that if you increase the sensitivity by factor of 2, you increase the sensitivity to the distance by factor of 2. And if the distance becomes larger by a factor of 2, volume increased by a factor of 8, almost 10. So only factor 2 increase in sensitivity gives you 10 more events, 10 event rate. So we are expecting a lot more. For example, in this LIGO detectors up to now, essentially they detected more or less 1 event per 1 month or 2 months. But this will, in the next round, it will be like 1 per week. Yes, then you will be able to do some astrophysics, and cosmology becomes interesting. Now, since I'm from Japan, and I do have to touch on what is going on in Japan, which is we do have some Interferometer project going on, and which is almost in completion. It's called Kagra, and Kagra is a meaning. Well, I don't know how you pronounce this in Chinese, but then we pronounce this Kagra, meaning difficult music. So that's a very nice. I mean, this gravitational. We have just heard this. Well, as I said, maybe not in music, but this. So that's the kind of the music from the heaven. Anyway, so this is Kamioka. Kamioka is the place of this detector, and actually it's famous for the super Kamioka, the neutrino detector. And this gravitational wave Kagra detector is placed under the ground and with 3 kilometers arm length. So it's a bit shorter than LIGO, so this means that the sensitivity is a bit worse. But instead, because this is placed in the underground, they are free from all this sort of ground noise, so-called seismic noise. So, and at the same time, they will cool this detector down to about 10 Kelvin or something. So this means that you can decrease the thermal noise by about a factor of 3 or 4. Thermal noise usually goes by square root of temperature. So, if you go down to this about 10 degrees, then Kelvin, and then it's about maybe a factor of 10. Sorry, no, factor. Yeah, it's a square root of 30. Let's say is 6, 5 or 6. So that's the maximum. But anyway, so this is what they're able to do. And they are actually almost completed, and they have just, they're actually doing very, very well. And hopefully to start the full operation by year 2020. And the hope is that this beginning of this full operation will overlap with this second, or third operation run by LIGO, which will start next year. And then you can do this joint analysis, joint detection, and that will be very, very interesting. Anyway, so the future of this detector network, which we call Gravitational Wave, International Gravitational Detector Network, will be like this. So right now we have this 2 LIGO detector. Actually, I will talk about this Virgo, but this Virgo is the Italian, French coalition, and they started operating about a year ago, and actually they joined this LIGO detection, and they made a very, very important contribution as well. Hopefully the camera will start operating in the year 2020, and so we heard that actually the Indian government approved to have the detector, gravitational detector, exactly the same as LIGO, and so it is called LIGO India. Hopefully this will be finished by sometime in the middle of year 2020. So in the end, by the, say 10 years from now, if everything goes very well, then we have 2 LIGO detector and 3 others. Altogether, it's the 5 very large scale interferometric detectors. Having 5 detectors is very important because having 4, you can measure polarization of everything. And having 5 at the same time, you have redundancy in the observation. And the redundancy is always very, very important to cross-check and take correlations and so on and so forth. So hopefully everything goes well, then within 10 years or so, you'll have real gravitational astronomy or cosmology. Okay. The important thing about this, why the increase of number of detectors is so important, is actually presented by this figure. So about this angular resolution. So as I said, in the beginning we had this LIGO detector, 2 LIGO, and which first detected this gravitational GW170817. Signal to noise ratio, this is the ratio between the amplitude of the signal to the noise level. And if this is large enough, then you don't have to worry about noise, you just immediately see this the signal. And as you could see, the beginning is, we have already seen that the signal was quite clear. And this signal was the signal to noise ratio of 24. Okay. If it is beyond 20, usually you can easily see by your eye. Now, just last summer, they also detected gravitational events, but which was the signal to noise ratio was not so good. Together with Virgo, so they used 3 detectors. So this is a combined signal to noise. And even you combine these 3 detectors, signal to noise ratio is lower than the first one. But if you look at angular resolution, this was the first angular resolution. I told you that because of 7 millisecond difference, you essentially know from where it came from, which direction it came from. So this is the kind of the directions in the hemisphere, sky, which they can say, predict. But anyway, so this is so huge. But if you think of this, in this case, you have 3 detectors. Once, as soon as you have one additional detector, all those signal ratios low, angular resolution increased maybe by a factor of 10 or even more. So having more detector really increases the angular resolution. And this actually means that if you have more and more detectors, you really can do astrophysics. You can just pinpoint the source, and you can look for some other events from some other electromagnetic wave or something and see what is happening there, or maybe identify the source galaxy, and all these things you can do. With this size, you cannot really do, but as soon as you go down to this size, there appears possibility. And if the detector number increases, this goes even better. So what's next after binary black holes? And probably you have already heard that last summer, right after they have detected the black hole events, they also detected binary neutron star events. So they said LIGO did it again. Anyway, so this was, and actually it was, I don't know if this was on purpose or not, but it was announced right after Nobel Prize. Nobel Prize for them was announced, yes. But anyway, so this is called GW170817, means that the 2017, August 17 event. On this day, they observed the gravitational wave, and the signal ratio 32. Now you see that compared to this 24, it's even 10 times bigger. So this is a really strong event. And the reason why it's so strong is that it happened so close. Remember that in the case of this first LIGO event, it was 400 megaparsec. This is 40 megaparsec, 1/10. It's very close. Again, they are so lucky. I don't know. Maybe there's somebody is controlling this universe, giving some gifts to them. But yes, so it was very strong, and from the waveforms and so on, they could expect there to be a neutron star range. Mass must be compact, and range is neutron star range. But this is only with this, you cannot really go beyond. Maybe these may be a black holes, very, very small black hole. That you cannot really deny. However, actually, at the same time, they saw the gamma ray events from the same source, same direction, and which occurred about 1.7 seconds. And after that, they started do this follow-up observations in various wave frequencies and so on, and perhaps being able to see many. But first of all, let me just go to this gamma ray thing. So this is gravitational wave 170817 is equal to this. GRB means gamma ray event. The gamma ray is 170878. A means that maybe later sometime we need to this level again, but when you see some events in the first, on that day you put A. In many cases you might see the say gamma ray events twice a day. In that case, you have the B, C, D, and so on and so forth. So this means that if we have maybe more than 26 events per day, I don't know what they do. Maybe they add something else, or maybe use Chinese letters, yes. But anyway, so this is the rule. So far for the gravitational wave, we don't have this, but maybe soon, we have to add some subscript. Anyway, so they simultaneously detected the events, and the difference in time was 1.7 seconds. And after the gravitational event, and this is consistent with standard picture because usually the electromagnetic events will occur on the scales outside some events, and so there will be some delay over time, which is true for the supernova and everything. And first, this interacting wave comes first. So gravitational wave comes first, and then followed by electromagnetic waves. And anyway, the distance was so close enough so they can really see this galaxy. And now, here's another sound. I hope it works. This last thing, I guess it's just, I don't think the gamma ray has any frequency which we can hear, but so just for the fun. But anyway, so this is exactly what they see. So you have the gravitational events right after that, 0.1.7 seconds after they saw it. And after that, of course, everybody starts to measure, and since we know, when you know, in astrophysics, astronomy, when you know where to look for, then you can do many things, right? I mean, usually, if you don't know where to look for, it's very, very difficult, because usually the what do you call the size of the size of the sky you can cover by just looking at through some telescope is very, very tiny. So you cannot really see the whole sky at the same time. But if you know where to look, you can look. And then you find that, for example, first we have this gravitational wave gamma ray, the X-rays at the series, the ultraviolet frequency, optical frequency, infrared, and radio. On all frequency they saw the waves. Yes. And which, all this sort of observation is completely in agreement with the predictions, theoretical prediction that after neutron star merging, you have some disk forming, and then you have some shock propagating that way, and you have some nuclear synthesis occurring, and waves are emitted. Then the electromagnetic waves are lower frequency waves are emitted, say, a few days or a few weeks later, and so on and so forth. And everything matches with the theory, and this made sure that this was indeed the coalescence binary neutron stars. And this is amazing that actually, this is again from LIGO site, that 70 different observational groups, including 7 satellites, all over the world joined together to measure this event, and they contributed to the revelation of this source, astrophysical source. And which is called multi-messenger. Multi-messenger means that they are not only just one frequency, one waves, or one kind of waves, for example, electromagnetic waves, but in this case now we have the gravitational waves. In future, hopefully we also add the neutrino detectors. Then in the end, we may have multiple multi-messenger astronomy, and by which you can understand many things, including this, for example, the equation state of neutron stars, or maybe high density nuclear matters, or maybe some information about modified gravity, and so on and so forth. So then you can do many things, and so this is a very, very important step. Now, so let me just talk. Up to now, I essentially talked about astronomy, astrophysics, but think about cosmology. And one very, very interesting sort of result from this neutron star coalescence is the estimation of the Hubble parameter, or Hubble constant. As probably you know, that our universe is expanding, and well, 40 megaparsec is very close enough. So this standard Hubble sort of law is valid, and it means that if you go from us, if you go deeper in space, then those galaxies recede faster. And this proportionality constant called Hubble constant. And the important thing is that this velocity, or the receding velocity, essentially is measured by so-called redshift. And redshift can be very easily measured because we know the atomic spectrum and everything on Earth. And assuming, because this is a very good, important assumption, but since there is no evidence that this is wrong, so we do assume that physics is same at that neutron star at the 40 megaparsec away. If the physics is the same, you know this, how the spectral lines are distributed, and by measuring the slight change of the position of those spectral lines, you can measure redshift. So redshift can be measured to a very, very high accuracy. But distance is not. Distance is very difficult. Distance, for example, in our case, let's look at somebody over there and see how far you are, or somebody is there. Then, first of all, you have to know the size, actual intrinsic size. For example, in our case, we say if human being are kind of standard candles, we say, then if you see somebody who is assumed to be, say, 1.7 meters height, plus minus 20 centimeters, something, and then within this, then we can actually measure how far he or she is within this 10-20% accuracy. But maybe somebody who is sitting there is just a small dog, or maybe a giant. In that case, you make a huge mistake. So measuring the distance is very, very difficult. So that's why to draw so-called Hubble diagram, you need thousands of, actually millions of galaxies, yes, and calculate by various. Combining various data, calculate the errors and so-called systematic errors, and draw a line. So this is what you do, and this is how they obtain the sort of number, which is still about 70 kilometers per second per megaparsec. Means that at the distance of 1 megaparsec, a galaxy is receding about 70 kilometers per second. Very fast, but still finite. Anyway, so this is the kind of the standard thing that you do in astrophysics or astronomy. But in our case, we have now seen this gravitational wave from this binary coalescence. Since we know where it comes from, the redshift, again, can be very, very accurate measure. Now, how do you estimate distance? This is very, very simple because, as I said, gravitational wave decreased by factor 1 over r. So by measuring the amplitude, which is exactly what you have seen in data, you can immediately tell the distance. Of course, in this case, it's not so. The only remaining ambiguity is so-called the inclination angle. And for 3 detectors, it's not so easy to determine the inclination angle. So they have some error bars, and because of this error bar, you have this accuracy. But still, important thing is that with just a single event, of course, with a single event you cannot draw a line. So to add to this sort of data, you have to assume, say, a cosmology and so on and so forth. But with given such a background cosmology data, then the accuracy measurement is already this is essentially the error bar in the distance measurement. Distance is measured within 10%. It's one point, one single point, give you this accuracy. Now think about some 10 years later future where we have maybe this kind of events once a week. So 50 events per year, and within 10 years we have 500. This will definitely change cosmology. Okay? So you will have a completely independent new way of determining Hubble parameter. And then we may have, I don't know, there's so-called Hubble parameter attention that this Planck satellite, which gave us a very, very accurate map of the universe, but when the universe was born 300,000 years later after the birth or something, and they predict some number of the Hubble parameter, while this current measurement tells you it is, I forgot which direction, it is probably around 70, 71 or 72. So there is some discrepancy, it's at least more than 1 sigma discrepancy. And whether this is just due to systematic error, or maybe due to the specialty of our local universe, or something else, we don't know. So this will be perhaps solved within 10 years or so. Okay, so another very, very important thing, this 1.7 second difference. Although we think this 1.7 second difference between the detection of gravitational, the final coalescing time of gravitational wave to the detection of gamma ray burst is due to the geometrical structure of the source. But if you ignore this, then at least this means if you just assume that this came from the same point at the same and emitted by at the same time, then this means that the gravitational wave propagates a little bit faster than electromagnetic. And this little bit faster, but it's very small because as we know that it came from about 0.13 gigalight year, which is about 4 times 10 to 15 seconds. So they propagated the time of 10 to 15 seconds, and the difference was only 1.7 seconds. So this means the fractional error in difference of the velocity will be 1.7 seconds divided by this number, 10 to minus 15. 10 to minus 15 times 10 to 10 centimeter per second gives you 10 to minus 5 centimeter per second. So the propagation distance, velocity between these two must be less than this. And this is a very, very, very strong result which we have never had, because we have never had any gravitational wave events so far. So this is the first thing. We can measure the propagation speed of gravity and propagation speed of waves. And this kills lots of so-called modified gravity theories and lots of dark energy models. So by this single event again, all this sort of variety of dark energy models we discussed about just all excluded. They just all went away. So you see, this kind of thing can happen, and it's very important. So even a single event can do a lot on cosmology. If you have many, you cannot imagine what we can do. So let me just talk about future project. There are some future projects on gravitational wave in space detectors. I know that there are some detector plans by China, but since there are two competing projects, maybe I shouldn't mention any, to be fair. But anyway, the one which we have in Japan is called the LIGO. This counts Interferometric Observatory. The average is somewhere in the middle, it's about 1,000 kilometers. Hopefully it is launched by sometime in the year 2030s. Frequency is 0.1 hertz, so it's by the way, so LIGO and all these ground-based detector has the best sensitivity around about 100 hertz. So this is down by a factor of 1,000, which means that actually a frequency is proportional to frequency. Wavelength is proportional to the mass of the system when we talk about gravitational waves. So this means that these can detect some waves from like 1,000 solar mass black hole coalescence and so on and so forth. Or maybe you can just see those in spiral phase long before those compact binary coalesce. Anyway, so this is the LIGO, and also this LISA, which before LIGO detection, actually, the NASA stepped down from LISA, and they changed it. The European Space Agency had to shrink down the original idea to so-called E-LISA. But now, thanks to this LIGO, NASA decided to join again. So LISA is back. and this will have this 5 million kilometers armlength. It's amazing. I mean, it's not the standard type of pulsar interferometer, but still, so it will be sort of and the 3 actually triangular configuration, and the frequency will be about 10⁻³ hertz. So this is further down by a factor 100 from the LIGO, or maybe a factor of 10,000 or 100,000 from the LIGO band, which means that you can actually see some very, very supermassive black hole events in the sky. So, another thing is so-called pulsar timing array. As I told you, that the pulsar is a really, really accurate sort of time clock. So any small deviation from the standard sort of clicking time, this is called timing, pulsar timing. It can either be due to the fluctuation in the source or something else. And one of something else will be gravitational waves. If the gravitational wave propagates through the space between the pulsar and us, and then this will stretch the timing slightly, or give you some fluctuations of the timing. And if you by measuring this, you can detect gravitational wave of very, very low frequency of about 10⁻⁸ hertz, which is a period of 10 years. This actually means that you have this arm length of about a few light years, arm length interferometer. So anyway, and of course in this case, just single pulsar doesn't give you much statistics, but adding many pulsars, then you can increase the sensitivity. And this is ongoing, and we hope to be able to see something from this pulsar timing array. So altogether, these are called multi-band or multi-frequency gravitational wave astronomy. So from about 100 hertz down to 10⁻⁸ or 10⁻⁹, a period of, let's say, 100 years down to about 1 millisecond or so, 1 second or 1 millisecond. Well, we still don't have any detection on that side. I'm talking about the other side of the data, but anyway. So this sort of high frequency, actually, gravitational waves is an unexplored region, And if something can be done here, that will give us much more interesting observational data. Anyway, let us now turn to gravitational cosmology. So one thing which is being predicted by so-called inflationary universe model, and which we do hope to be able to measure it within a few years, is the gravitational wave from the vacuum fluctuation of the inflationary space-time. And this will produce not only a fluctuation in the temperature perturbations, but also fluctuation in so-called polarization. And this detection of polarization will be the real, evidence for what was happening during the inflation. Meaning that at the same time, it will be the first confirmation of quantum gravity, because all these fluctuations are when you compute it based on quantizing the space-time. So this is a quantized gravitons in that sense, on a very, 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 very low frequency or high or long wavelengths. In some sense, these DMOs, so-called, and they will produce some particular polarization patterns in the sky, and if we can see them, and if we can identify them as primordial, then you detect a gravitational waves from inflation. In some sense, yes, since you use the whole sky, and this sky is the CMB map of the sky with the size of our current horizon scale, which is about 10 to 28 centimeters or so. So this, in terms of light year, it's about 10 gigalight year. So in some sense, you have the detector size of 10 gigayears. So in this case, of course, you cannot see the oscillations of waves. It's not the pattern, just frozen pattern. You see. And so maybe, well, this is new some project to detect B modes, and this LIGO, which is led by some Japanese group plus some US team, is hopefully to launch by year 2030. And actually, I have to say that because I'm from Coventry Institute, this is one of the main institutes to support this project. Hopefully, things goes well. Okay, and also, you know, in the early universe, you can think of many other different sort of epochs where the gravitational wave may be detected. One of them is, this is still under debates, but the possibility is from so-called electric phase transition. So this transition, maybe transition is very strongly first order. And in this case, you have lots of sort of so-called bubbles, which are gliding or created, say, very dynamically. And they can, like this is just a picture taken from this paper. You may produce some amplitude gravitational waves, and which may hit, this is the VISA, I think this is VISA, this is the this is square kilometer array future project, I guess, or maybe a pulsar timing array. Anyway, so at the frequency of light 10 to minus 7, the 10 is 2 Earths. So maybe there are some cosmological sources, and if you actually see them, this is a very, very strong indication that in the very early universe, you know, this electric phase transition was first order and had this kind of events. Okay. So you learn physics, of course. And so altogether, so we have this term of gravitational cosmology. As I said, you know, by single event you can do quite a good cosmology, but in the future you probably see a lot more about cosmology. And cosmology extended, of course, to a period of, as I said, 10 giga-year, and which is observed by CMB mode. And then on a sort of a high frequency level, where, as I said, maybe we have some gravitational wave from phase transition in the early universe. Maybe there was something else, we don't know. So maybe if something else interesting is happening in the early universe, it might even be detected by LIGO and advanced LIGO, you know, which will start operating next year. Actually, this will be a noise. It's like when people discovered the cosmic micro background by Penzias and Wilson. If you try to reduce the noise by, you know, all these technologies and so on and so forth, and we currently, as I said, the LIGO people try to decrease this noise by factor 2. But at some point, maybe they see something which cannot be decreased. And if it remains forever, then in the end, and if it is seen in other detectors as well, then this is a strong indication that it's really a cosmic background. So maybe in the near future you see a cosmic gravitational wave background, which is, and maybe even you can talk about cosmic gravitational wave background anisotropy and so on. Maybe polarizations, you know, many things. There are maybe very, very interesting sort of future of cosmology. Again, let me just go back to this figure and say that yes, by using gravitational wave, you can sort of see the universe, the history of the universe at various epochs. And when there are some very violent phenomena happening, the gravitational wave will be emitted at certain epoch, and then from such epoch, the waves from such may be detected by future detectors. So this is the last slide. So gravitational waves are an indispensable tool to explore the unknown universe and discover new physics. And what will be discovered next, we don't know. Stay tuned. Thank you.
Thank you for a very interesting, exciting talk. Now we open to questions. Any questions? You can use a mic here.
So very interesting talk.
Thank you.
Specifically, in the multi-messenger, the time arrival difference between electromagnetic and gravitational, how does one relate it to the dark energy issues? Yeah.
Oh, yeah, well, there are many dark energy. If it is just simple dark energy, it's considered to be, say, cosmological constant, nothing more. But nowadays, people talk about dark energy as effect of modified gravity. So rather than adding some unknown matter on the right hand, the Einstein equation, you modify the left-hand side of the Einstein equation. But if you modify in a sort of general way, you end up with finding that the speed of propagation of gravitational waves is different from electromagnetic waves. And this depends on parameters of theory. But because of this, essentially, I don't exactly know, they had like maybe 5, 6, 7 parameters, out of which as far as I know, only maybe 2 remain.
So it's actually any theory that gives you the propagation of gravitational wave different from C would fall into that category, right? Not necessarily just the dark energy.
Oh yeah, that's right. No. So essentially any theories, but especially in these days, people talk about dark energy as a type energy model because they consider modified gravity theories. Because the modified gravity can give rise to the accelerations of the universe.
Yeah.
So that's a kind of application of this modified gravity theory.
Yeah.
Yes.
Thank you.
So very nice talk about the Hubble parameter, Hubble constant. So you mentioned this 10% error because of the inclination and other things. But you also mentioned that there will be more detectors and then there will be more detections because of the sensitivity increase. So now in astronomy, like supernova or baryon oscillations, the errors of the Hubble constants are getting down to a few percent. So if the gravitational wave want to go down to few percent level, what do you need to do? When are we?
So I think it's if the number of detectors increases and then you see all the polarization patterns and so on, then you begin to see. I mean, you confine this inclination angle to much better accuracy, perhaps. Yes, that's one thing. So each detection can give you better accuracy. Then, apart from that, the whole point is that the gravitational wave doesn't have essentially any other systematic errors. Like in the case of supernova, you do have systematic errors which you cannot control from us because we don't really know whether that supernova is the same as our supernova. Okay, so in that sense, when they say they go down to this 0.2% or so, in the case of supernova, it's just because it's so distant. And you just assume you have a proper physics. You assume you know the proper physics. Then you can sort of squeeze the Hubble parameter because if you point some point far away, and if you say that the error is small, then the line becomes straight, which gives you a smaller error. This is, I think, the case of supernova. In the case of baryon acoustic oscillation, it's the Hubble parameter essentially related to the expansion of the universe until, say, redshift 1 or 2. And what we see in this Hubble diagram is essentially a Hubble parameter up to redshift 1, or local universe. And this is where the so-called tension of the Hubble parameter exists now. And whether this tension is real, and we have a different sort of Hubble parameter in a local universe than from, say, Planck or the EAO observation is a very interesting issue, and this is definitely within 10 years or so we may not have a final answer, but we have a very interesting clue to answer that question from the gravitational wave detections.
So, but for gravitational wave detectors also, if you go too high redshift, you have to worry about the gravitational lensing, because you are biased to the brighter sources. So I saw one.
That's very interesting. Yes, I think yes. So probably yes. If you go to redshift 1 or 2, yes. But so as I said, I mean, let's say focus on our local universe up to redshift 1. Then the lensing probability is fairly low. I mean, maybe you have some strong lensing in it. That itself is very, very interesting, by the way. But so probably at leading order approximation, you can ignore the effect of gravitational lensing, and then if you have sufficiently large number of data, as we had just a few months observation, and we saw this event. And if you increase the detector, sensitivity by a factor, that means factor 2 means that we have factor 1. So right now, actually, the sensitivity to measure neutron star binary is up to about 100 megaparsec at most. But if this becomes 200 megaparsec, then you increase the volume by about 100. 10. No, 10, yes, by a factor of 10. So the rate will be increased by a factor of 10. And this will give you much better, has a statistics, right? And 200 megaparsec is our local universe yet. I don't think gravitational lensing is so good.
So for detectors, do we have to go down a few percent for international, or do we need LIGO India?
Oh, that I don't really know the quantitative data, but yeah, I don't know. Sorry, yes.
So why do you think the black holes in the GW170817 event might be from very universe?
Oh yeah, well I didn't have time to talk about that. Including the other events which they measure, and those, especially the ones which involves heavier black holes, like 20-30 solar mass, and they measure the so-called the effective spins of those black holes. Of course, it's a sum of spins, so maybe you have two spins, in the opposite direction and sum up to 0. But if you assume they are sort of randomly distributed, you would expect the black hole spins to be very large, especially from the collapse of standard stars, because any small oscillation, rotation, probably that becomes very rapidly rotating. This is the scalar effect, when the angular momentum conservation. But if it is observed, it is produced in very, very early universe, then all these so-called primordial black holes is supposed to be essentially non-rotating, because there's no rotating effect on the size of what we call the Hubble horizon scale. So the data, although it's still just 2 or 3 binary data, they indicate the spins of those black holes seems to be unusually small compared to what we expect from astrophysical events. So that's the one of the reasons. But it's very, very not yet. It's not it's a kind of indication, not really evidence yet.
In terms of the gravitational cosmology, so to find out the optical electromagnetic counterpart is very important to measure redshift. But in the case of binary black hole, people don't expect very much electromagnetic field, so it's still very difficult to identify the exact redshift or exact location of the sky. So how do you use this binary black hole system to do gravitational wave cosmology?
Right. So in this case, it's the only thing we understand is the kind of apparent magnitude type thing, apparent some distance or the frequency and so on. And you have this redshift effect, and also, so the mass is the proportion to the redshift, in fact, or inversely maybe I should say. So that as you go deep in the redshift, then because of redshift, the frequency becomes lower, and then it looks more massive, yes, than actually it is. So you have to take into account all these things, but the important thing is that depending on your scenarios, for example, the scenario of star formation, maybe population of 3 stars, genesis, or maybe this primordial black hole models, you have a particular prediction for the merger rate. And this can be measured. You know, if you accumulate, you know what the rate of those mergers occurs. And maybe you have some anisotropies and so on and so forth. But we would expect, if this from some very large, long distance, the distribution to be homogeneous in the sky, like the gamma ray burst. So you get some cosmological information from that. So of course, I mean, that's not enough. We do need neutron star binaries as well.
Oh, yes, thank you very much. I have the question. Yes. So you mentioned about the detection of gravitational wave at a higher frequency would be even more interesting.
Yeah.
Can you say a bit more about what kind of physical phenomena we would expect to see, or what kind of challenges in the putting the detector?
Well, well, this is related to the inflationary model, and if you go back further down and deeper in time, then frequency of those waves generated at that level is much higher and higher. And the highest frequency we expect will be about megahertz regions, which if we actually see it, it will be from some phenomena at the end of inflation. So this is a very, very interesting sort of possibility. But of course, for the moment, we don't really know what to do.
What's the challenge in building the detector?
Since I'm not the experimentalist, I don't really know. I mean, but if you think about the megahertz, then the size you need is small. So you can probably produce tabletop kind of detectors. And maybe if you place this, a 1 meter interferometers on the table and just place all over the Earth, or something, if you have a sufficiently large number of them, maybe there's a way. But I have no idea. No, maybe you have to go to the moon. But this is definitely an interesting sort of area which has not been explored yet. I mean, not too much.
As we go through, the early years, of course, the stochastic gravitational wave background has been there for a long time for theorists. Is there any prospective experiment designed specifically for that purpose, the primordial gravitational wave?
Yeah, this is the light bulb actually. So where is it? So this is the light bulb, which is probably you know this so-called famous R. This is the ratio of the tensor polarization amplitude to scalar polarization amplitude. And of course now we completely ruled out this R for 0.3. But if this R is 0.01, if there's any thing like this, then this is the expected amplitude of gravitational wave. Light bulb sensitivity is here. So you will definitely see those so-called ionization bumps, and which any direction of waves, I mean primordial waves around these regions, just means that those are from early gravitational.
Is it stochastic in nature?
Stochastic. If what we believe is yes, because this is just from pure quantum vacuum fluctuations. So the phase are stochastic. Yeah.
But it's not particularly designed to see the stochastic nature of the kind. I mean, I also have some comment because most people will say if you see the B mode, then quantum gravity is there. it's really just the quantized gravitational perturbations. I mean, I don't think it has anything to do with Planck scale physics. But if someone wants to see Planck scale physics, is there any way at all? I mean,
no. So this, I'm not talking. Sorry. So in that sense, this is nothing to do with Planck scale physics. This is inflationary physics, which is by the scale maybe down by the 10 to minus 5, yes, from the Planck scale. So it's in that sense, space-time as a whole is essentially classical, no real Planck, beyond Planck physics, Planck scale physics. But the important point is that, as you say, that this is due to the quantization and of space-time fluctuations, which has not been seen until now. So this is in that sense direct evidence of quantum gravity. Yes, I mean it's the effect of quantum gravity. Let's say. Gravitons, yes. The existence of gravitons. Gravitons. Yeah.
Last question. Okay, last question.
So if in the universe there's a first order phase transition and gravitational waves produced, then what kind of signal should be seen on CMB? For example, in the TT spectrum of BMO and EMO should be measured?
Well, so unfortunately, in that sense, unless this transition they occurred very early in the phase, during the phase of inflation, which probably was not. I mean, maybe, but so the scales you expect from the phase transition and the gravitational waves from those phase transitions, let's say after inflation, is somewhat very at say high frequency compared to cosmological frequency. And on this frequency, if you just see CMB, I mean even just simple CMB, temperature fluctuations totally contaminated by local physics, and BMOS totally contaminated by the dust, I don't know, whatever. And you don't really see anything by CMB. So here, the only way is to detect the gravitational wave directly. It's not through any other sort of events in the CMB or anything.
So because of the time, so I think we have to finish now. But if you have any questions, there's a tea break outside, so you can keep asking. Thank you.
Thank you very much.